So yesterday I started to talk about Hughes model. I would like to come back to it since it's quite a sophisticated model actually, which is very difficult to analyze from a mathematical standpoint. I will not go into details, but let me remind you what it was. So the crowd density described by rho, x depends on x and t, and you have a transport equation, dt rho plus the divergence, and a term that I will explain, gradient phi over the modulus of gradient phi, and then I can write that way, v of rho, So this is the velocity, the global velocity, which transports rho, the people, the crowd. And v of rho is a scalar number, which gives you the speed with respect to rho. So typically v of rho can be, well, depend. In this context, it's usually written like that. It decreases when rho increases typically. So it can be, for example, 1 over 1 minus rho. I take the reference velocity to be equal to 1. It's not very important. And then phi is a solution of a so-called aconal equation. That is this, as I said yesterday, bizarre equation, that's not 0, is typically 1 over v of rho. So what does it correspond to, this equation? So you see there is no time derivative. Basically, if you are in an evacuation situation like that and you have some density at some point, this phi, you will put boundary condition here on the boundary phi equals 0, meaning that the distance to get to the exit is 0. When I say the distance, it more corresponds to time actually. The time to the exit is 0. If you are here, you are at the exit. And then let's first consider the case when you take v of rho is constant. So the velocity, the speed does not depend on the density. In that case, it will give you actually the geodesic distance to the exit. So there is no boundary here, so you will have something like that. And I will show you some pictures. This is the basis of most crowd simulation. You need to have a desired velocity field, and usually you compute the geodesic distance to the exit. So here you have 0, and then 1, 2, etc. So that was for v of rho constant. But if you account for that with a velocity that decreases with rho, it means that it can be shown that this value will correspond to the time taken to get to the exit along a path, along which at each instant your speed is v of rho, you see. So what will happen? It will deform. It's not so easy to improvise this, but let me, perhaps it's easier to draw the path line. Basically, you will have shorted paths, but associated to this velocity, that will go like that. You pass. You avoid zones when there are some people. Okay, so it's quite a sophisticated model. What does it say? It's basically say so. And again, when you have gradient phi, it just tells you that the velocity goes along the direction you took. So it's supposed to have you avoid highly packed. So yes.
So that's the definition of phi, or is it a property? How do you define phi?
Phi is actually the solution to this equation, which is bizarre. It's difficult to study this aconal equation, but you can show that it's well posed under some conditions. So phi is defined by that. And then you get it and you put it here and it gives you the direction. And let me perhaps say one word. Sylvain might talk about that this afternoon because it's made in Chromosim, the software package. It's solved, and basically it's solved in a frontal way. It's a PDE, but very special PDE. And basically what you do is it's quite enlightening to understand how it's computed. You set phi to be 0 here, and then you use a Cartesian grid, and then you update the value in a frontal way. and you go from here to here. And if it's constant, you will have something like that, what I drew it first. But if V depends on rho, then you have these deformed path lines, etc. So you can solve that in a fast way, actually, by this frontal way. It's a bit difficult to implement, but it's done in chromosome, you see. So it's very difficult to study. As far as I know, there is no full mathematical framework, result or existence of uniqueness in 2D for this equation. It's complicated because you have a coupling between those two weird equations. This is not weird, but it's difficult to study, the transport equation, and this is clearly a bizarre equation. But it gives interesting result. There is one drawback with that, is that it relies on the fact that when you decide your strategy, so you are at some point, and this will give you the direction of your velocity. It depends on the instantaneous distribution of density. Let me show you an example. If here I have a room, let's say to spice it up a bit, with 2 exits, and here you have a bunch of people, and here another pack of people. Those, at some instant, they will see, okay, this is free. When you compute this equation, it will give you straight lines, so they will go straight ahead to the exit. In the meantime, those will go also, but they will arrive first, so at some time, this is here, okay? So this is not very efficient, because you get this V of rho that is smaller. So in that case, it might happen, if it's reproduced by this equation, that this pack will change their mind by getting here. So it's a bit bizarre, because there is no anticipation. Of course, if you see, you can imagine that they will get first, and then, so I think it's kind of similar to what you heard yesterday with you have to anticipate with this mean field game approach, which is based on game theoretical principle, and it's important. So there is no, in some way, there is no game here, and that's clearly a limit of the problem, because there is no anticipation. Okay? I don't know if you have questions about.
From a mathematical point of view, it must be a bit singular, this equation, to study.
It's singular. It's really a mess, because here it's not regular. Even for the when you have, for example, in this equation, when you have an obstacle and you compute the velocity, the shortest paths, some of them are not smooth, and you have a line upstream the obstacle where you have it's doubly defined, so you have something that is quite singular. Phi is continuous, of course, but it's not differentiable. And so you have this problem. It might happen that if you do not have strong assumption of the geometry, you may have lots of those lines which are complicated to handle. And as you probably know, this equation, the transport equation, I'm saying that for more than physicists, it's actually difficult to study. You may imagine it's the simplest equation you may imagine, the conservative transport equation. But from the mathematical point of view, as soon as this field is not very regular, that is Lipschitz basically, then it's very difficult to study, because you cannot properly define path lines or trajectories. Okay, so when it's coupled with a nonlinear equation, this is indeed a complicated story.
Sorry.
Yeah.
How do you determine the expression of rho 1 over 1 plus rho? If we have the exact formula, we could solve the equation.
Yeah. Oh, you mean this?
Yes.
This was just an example that is commonly used, but your question is?
Why we choose it, or what's the limitation of this one?
I guess, well, the results, there are 2 questions here from a mathematical standpoint. Basically, you will need, if you want to have some results, you will make some regularity assumption, so it's not singular. But your question was more about modeling the actual behavior. Yeah, this is something It's something that is well known in traffic flows. You heard about the fundamental diagram, probably. You see, you make measurement on a highway and you draw. So you have a density with a maximal density. And you draw typically the flux. You measure vehicles with respect to the density. And if you divide by rho, you have the velocity, which might look a bit like that, 1 minus rho. Okay, so some experiments have been made for pedestrian. I have to say that it is very complicated. What is done usually when you have people online, and you have like in a traffic flow, and there are some. I can show you some pictures. We wrote a book with Sylvain Faure, who is going to talk this afternoon. We got in the literature, you can find some such things for pedestrian, and you can fit the curves, and you can find expressions a bit like that. You see, this is a bit like 1 minus rho, like for small densities. So there is no, of course, analytic formula. And when you have people in a 2D, two-dimensional space, it's very heuristic. There is no straight. I guess if you plot all the relation between rho and v of rho, you might have something very dispersed and not at all a curve. So it's in pedestrian flow, a lot of things are done in a heuristical way. Actually, it's much cleaner in traffic flow actually, because there is when you have cars in line, it's much easier to control things. I hope I. Okay. Yeah.
Maybe I missed something, but what I don't understand in the equation is that it seems that if I change, it seems underdetermined, because if I change phi by minus phi, I just get the backward equation.
Oh. Yes, you have to. No, that's right. I thought about that yesterday. There is a problem of sign. Clearly, here you can change phi by minus phi. So you will have to put some more assumptions. Say, for example, you look for the positive solution to this. This is the distance, and in that case, you should actually put a minus. So it's some kind of gradient flow with respect to the distance to the exit. The distance modulated by the speed. Okay, sorry. Okay. Let me perhaps just finish by a last remark with a model that I could not see in the literature in a bizarre way, but it is very natural. I told you about the Helbing's model, the microscopic Helbing. Let me write it again. So it was du over dt with mi over ui minus ui, and plus some forces, interaction forces, repulsion forces, basically, J and I. Things like that, where those forces were typically when you have two particles, E, I, J, it's a force that is exerted in a repulsive way. And this is typically Fij, as I wrote yesterday, I think, is typically minus the gradient of some interaction functional Qj minus Qi with respect to, so Fji, so the force exerted by J on I with respect to Qi. And phi, if I'm not mistaken in the science, is a repulsion potential that decreases when particle gets closer. Actually, there is a natural way to write that in the macroscopic level. Actually, while preparing this conference, I searched in the literature. I couldn't find actually this model, but it's easy to write. I don't know why it hasn't been studied, unless I missed it. But you can write a macroscopic equation by simply considering d rho u over dt plus divergence of rho. This is exactly when you write Euler equation, when you write it, which express Newton second law. And here, when you have, if I write that, this is a so-called pressureless Euler equation, which is very singular. But here, since I am describing the system in the Lagrangian way. I corresponds to an individual. This is the total derivative, so it's replaced by that. It's less convenient to write it in a Eulerian way, but it gives you this. And here you need something, so let me put this in the right-hand side by something which would be natural, like rho of, to have something that is homogeneous. UI minus, sorry, there is no I anymore, it's just a macroscopic velocity. So you have some kind of frictional term, drift term, and then you have interaction, which are, you could put in the left-hand side, that would be more natural, and that could be something, or let me keep it in the right-hand side like that. That could be the integral was something like phi of x minus y, e x y with a minus sign, integrated against the density. So this corresponds to all the repulsion force exerted by other particles. Okay? So it's not very clean, sorry, but it gives you an equation, PDE. And actually, I found it in when I said that I didn't found it as a model for crowd motion, but it's something that has been studied by, for example, by Raphaël Danchin. I will not say much more because I'm not sure that it's a nice model to represent a crowd, but at least it's quite natural to write Raphaël Danchin. It's called the Euler equation with non-local pressure. So I'm not sure about the physical justification of that for gases, for example. Unfortunately, I should ask Laure, but I will, when she'll be back, I will ask her. And there is also a friction in the model. And actually, I do not know what, for him, what is interesting for Raphael, what he had in mind in terms of modeling for fluids, but for crowd, it's clear this is friction. If you have a zero velocity, then you get a frictional term. This has been studied theoretically, but not used to model actual crowd. But I might try to make some experiments, numerical experiments, to see if it makes sense. But it is really the macroscopic counterpart of the Helbing's model.
Gradient acting on phi in this?
Excuse me?
Is there a gradient acting on phi?
Sorry, this is not the same phi. Yeah, this is bad. This is phi here is not the potential. Here it was, so the notation, I should put the gradient with respect to x of some potential, which you integrate against the density. Is it okay? Or you will have to check for the sign, but I think it's that. And here is about the same phi. It's a potential scalar function, like a repulsive potential that is high when the distance is small. Okay? And it pushes away x from y. Okay? Using, okay. Sorry. So now let's get back to microscopic models. And I would like to, this is the main part of today's talk, talk about a granular model that we introduced some time ago with Juliette Venel. It is based, you will see, it is based on very basic consideration. It's very unsophisticated model, and actually that's what we had in mind. Mathematician, we do not like complicated things. We wanted the model without parameters, basically, because all the model I showed you, for example, Helbing's model, it has many parameters, the mass, friction coefficient, etc. And when I say the mass of someone, it's not intended to be the real mass. It's some parameter that you have to tune to fit to reality. The problem I would like to present you is there is no parameter, basically, just the global speed of people, some kind of reference speed, but that's it, as you will see. So the idea is the following. You consider the center of, consider n individuals represented by hard disks, Qi, Qj. And you write the distance dij. So if, of course, it depends. This is it depends. It only depends on the two position, but you write it as a function of all the position, the ij of q. And you would like to avoid overlapping, so K will play an important role. Is the set of all configuration such that dij, that is simply qi minus qj minus 2r is larger than 0. And r is the common radius. You might have different radii between people. You can replace it, these 2r, by ri plus rj, but this is not. I will simplify notation. Okay, so you would like to remain the people not to be at the same place at the same moment. And you are given, this is where possibly psychological modeling will take place, some desired velocity field, un, desired velocities. So here you can put many things, but I will stick mainly to very simple assumption, which makes sense in terms of evacuation. I will suppose, and that will be important in what follows, we will suppose that uj, it's not necessary for this model, but what we will assume that uj is equal minus the gradient, and we find this gradient flow structure, the gradient of some functional that I will write d, because it is a distance to the exit. So the setting is like before. You can imagine this distance function produced by a solution as a solution of the aconal equation. So this is the distance. We can add obstacles. Basically, this is the geodesic distance that accounts for obstacle or a complicated structure. And what it just says, so the gradient of this function is like that. You go in the opposite direction. Okay? And I do not put, I should put some velocity, some speed u, but I consider this 1. Actually, it's not so untrue. When you walk, your velocity is about 1 meter per second. So it's, you can imagine a 1 meter per second here.
Sorry, Bertrand.
Yeah.
So the distance from the exit is from the center of the exit, or just from
That's,
the line of the...
That's a complicated issue in the actual application. It can be the distance to a set. And basically that's what you should keep in mind, and that's possible with aconal equation. If it's a point, it's very easy to compute. You have a radial concentric field, but you can consider this, the exit considered as a set where the distance is initiated, it's considered to be 0 here, and then you compute the distance to that. And that's why here you have straight lines, and here this is, you see. So, yeah. And if you have, actually, Sylvain will show you some example. If you have another exit, then it might be difficult to compute. Imagine you have a room with obstacles and possibly many rooms and various exits. What is the closest exit? What is the distance? It's not so easy to compute. But with by solving this aconal equation, it's possible, and that's what is done by the software I told you about. So you will have a distance which goes from here, and then you compute progressively ISO values, okay? And at some point, they meet. So there is some kind of struggle, and you will have two gradients, basically, and you have some lines. If you have on the right, you will go to this exit, and on the left to this exit. Okay. Sorry for the picture; it's not very nice, but you can basically it's the distance to a set you would like to reach. Okay, and the model is the simplest you can imagine. So you have desired velocity, but some of them might tend to violate the constraint. So you might have at some point that two particles I and j are in contact, two disks are in contact. Let me write qj minus qi, qj minus qi. And you do not want that to get closer, because so you simply write that you have some set of desired, so no, not desired, but feasible or feasible velocities, CQ, that is the set of velocities such that whenever two particles are in contact, meaning that the distance is exactly 0, then I have some condition on the velocity. So it's something that you will find in any attempt to model granular flows using a hard sphere approach. So it's quite general, it's not limited to crowd motion. So you have Eij dot Vi minus Vj is less than 0. Okay? So this, for example, is feasible, okay? But if the opposite is not feasible, because it would lead to some non-zero overlapping, okay? And you simply write, the model is the following, is dq over dt is the projection on the cone of feasible velocities of the desired velocity, okay? So it's very, very simple. And actually, I thought it would occupy us a few weeks or a few days even. And it took, I have been working on that for about 12 years now. Well, not only that, but it's actually, I will try to show you that it's quite rich and interesting. And perhaps the most striking thing is that Laplacian operator is hidden somewhere here. It's not so obvious because it has nothing to do with diffusion. But there is a Laplace operator that plays a prominent role in this model, and that will be what I will talk about today. So let me first say that a priori it's not too complicated, at least to define this projection. So this is for each couple of particles in contact, you have a linear constraint with an inequality constraint, meaning that you suppress half space. So this is an intersection of half spaces, closed half spaces. So this is a polyhedron. It's convex, closed. There is no problem. The projection is well defined at each. Why is it not so simple? Is that the depends, you know, when you have an equation like that, you might think that it fits in the standard framework of ODEs, ordinary differential equation. But if you write that as dq over dt f of q, the problem is the dependence upon q is very singular, and it's something that you will find for any granular model with the hard sphere. That's one of the difficulties you get when you deal with hard spheres. You might have a situation when there is almost no contact, and then suddenly there are many. In that case, there is no constraint. This is the whole space, and you have dq over dt equals u. And then suddenly you have thousands of contacts, so you reduce cq, and it's very abrupt, very singular, and it changes. So you probably know that if you want to have well-Posnay solution results for this kind of equation, you need some kind of regularity. That is the Lipschitz regularity. Basically, it's almost C1. And here, of course, it's not C1, but it's not even C0. It's not even continuous, the dependence. So you are far away from using. So it might suggest that there might be many solutions. And we'll see that it's not the case, or not give the full proof, but for some bizarre reasons, the problem is actually well posed. And I will not say too much about the well-posedness. It's in the papers. I put some references. I think they are not yet in the web page, but if you go to the talk and then to the right, you click it, you have a list with downloadable, and the proof of the well-posedness is in one or two of these papers. But what I would like to insist on, I would like to focus on results that have a physical, that helps understand the system physically. So that's why I will talk more about the Laplace operation. that is underlying. Yeah.
So with respect to this singularity, if you have something a little bit smoother than just hard sphere or hardcore interaction, does it help or just shift the problem?
It's always the same. There are two in when people do with granular flows, they talk about contact dynamic, that is that, and or molecular dynamic. You can, of course, replace it in some way by some short range repulsion force. This is a different philosophy. Basically, what people do in computation is mostly like for when they do Helbing's model, when they want to handle this congestion problem, they do that. And actually for granular flows also, when you want to model sand, piles and things, you have the two philosophy, the two is possible. I am more comfortable with what I'm going to talk about, that as you can imagine, but it's possible to do the difference. What bothers me is that when you have a short range interaction, you have a parameter. You have to have some parameter that is typically the stiffness of the repulsion force, and you might have, if it works with 10 people, it might not work for 1,000, then you will have to tune it up. I don't like that as a enumeration, but it's even worse for granular flows, for example. That's what people do when you want to handle hard spheres, when you want to handle contacts. You can handle them by adding this short repulsion force, or considering that particles or balls are slightly elastic. But what is bothering against the problem of stability, if you deal, you will have something elastic bounce with a very small, high stiffness, small time step. So numerically, you will have to reduce your time step very drastically, like perhaps 1,000 times more than one. So you deal with things locally, and that will have, you miss the Laplace operator. I would like to show you. If I do that, there is no, I cannot continue my talk, but it's just a reason, but it's also about philosophy. But, and what also, last thing perhaps, the argument that people use to justify the use of molecular dynamic method is the reality is never, it's exactly the discussion we have. In reality, people or balls, even metal balls, they are never exactly hard spheres. But what happens when they do computation is that they use actually Poisson ratio, etc., that do not correspond to to the reality. Because if you consider like very hard spheres in reality, stones and things, if you use the right constant, then you will need thousands and thousands and time step to do that. Usually you do something, so it's not a proper justification, I think. And the idea also, well, again, perhaps the most convincing, at least for me, argument, there is no parameter, and you see, you really look at the limit problem, and without having to stress about this parameter that goes to zero. But it's possible, in practice it's possible to do both. And there is a limit also. You can show in under some assumption that the penalized thing with the little parameter goes to that. And that actually, even in Brézy's book for the 70s, Opérateur maximum monotone et semi-groupe de contraction, for those who might know, there is a very general results on equation a bit like that. And actually, to obtain solution, well-Posnay's solution, at least existence, he relaxes the problem. That's as if he was introducing this kind of relaxation. Okay, so I will say a few words now on. So I said that I do not want to say too much about well-Posnay's because it's a bit technical and perhaps not so interesting. But I will need a part of it, a little bit of convex analysis to go in this direction, and again to try to motivate you. It's something that some of you might not know, but to try to motivate. Each time you have a system which is non-smooth, so you have contacts, and actually even in Julien Tailleur, I think, talk, we saw some collections of particles of balls. So it's very useful to model things when you have this constraint, and they are everywhere. For example, the fact that this cannot cross the table is exactly the kind of tool that can be used to model that. So I'm trying to motivate you because it might sound a bit bizarre, this convex analysis thing. So the idea is to understand the mathematical structure and the problem, and also to get to this Laplace operator which I promised you. So the first thing is that K, how does it look like? The set of feasible configurations. So it's the set of disks which do not overlap. They might be sometimes in contact, sometimes not. And in the case, I will put an exit, but that is not important here. So it's something also. So it's like it's not a gas, but you have particle, finite size particle, but at a high density. That is not so far away from the maximal density. That's what is interesting here. So it's, of course, a high-dimensional space, but each time you have a contact, the set of configurations such that two particles overlap can be seen in a high-dimensional space as some kind of cylinder, you see. So basically, I will try to plot that in 2D. When you have, if you have a contact, A, J, you have an excluded zone that is convex, okay? And then you have the right to be here. This corresponds to the case where the particles are not in contact. Then you have other particles, another contact, and another contact, another contact. So basically your set looks like that. And that is a problem. You see that it is not convex, obviously. That is really bad. That's what explains all the problems actually that we have with grains. When you have those two configurations, if you take the mean configuration, you violate the constraint, okay? So it appears here, meaning you have two feasible configurations, but this one is not. So it's not convex, but we'll see it's not so far from being convex. Basically, it's the complement of the union of smooth convex set. So here you have singular points, but they are in the right direction. That will help, that will make everything possible. Also, this is oversimplified because I will show you some example, perhaps today or perhaps tomorrow, some example with grains or people when you have, let's say, 300,000 particles and perhaps 500,000 contacts. So you have to imagine a situation where here actually you do not have just two contacts, but a few hundred thousands of contacts. So it's a very complicated object. Okay? So what is important when you are at a situation when you have two contacts? For example, here, it corresponds to I have two constraints that are activated. Okay? Now perhaps I'm going to take this one, it's nicer. Something when you deal with this kind of constraint is the cone of feasible velocities. The direction that make you enter the domain. Okay? So this is a cone of feasible. And this is when I wrote dq over dt is the projection and cq of u. This is the cone actually. I am here, I can only go in this direction. And there is something that is, you can define when you have a cone, is the polar cone. So it's the set of vectors that have a non-positive dot product with all the vectors of the red one. Okay, so let me write that way. When you have a cone, the polar C not set of W such that WV is less than 0 for all V in C when I have a cone. Okay, so it's some kind of generalization of the orthogonal. When you have a linear space and you take the orthogonal, here it's the unilateral version of that. So if I take the CQ, this cone, this red cone, this polar cone, it's called outward normal cone. NQ is the CQ, the polar cone. Okay? So basically, let me give you some example. If you have an object which is like that, when you are on a point where it is smooth, you have half space of incoming direction, and you have just a half line of the normal cone is simply a half cone. So you generalize the notion of normal, outward normal vector or outward direction. Okay? And there is a property that was established about 50 or 60 years ago. It's actually not so difficult. If you have a cone, let me write it C. if you have its polar cone. So again, it's the set of vectors which have non-positive dot product with all this. When you take vectors, so typically you can imagine that this is the cone of feasible direction, and here is the outward normal cone, and here is the desired velocity. If you project it here, you find two things that are orthogonal, and you have an orthogonal decomposition. It's exactly in a linear, two orthogonal linear space. So what is written like that, you can write that the identity, or let me write that for any u is equal to the projection of CQ plus the projection on CQ naught. And those two are orthogonal. So I hope it's clear. It's quite natural, actually. You have the cone, and you make a decomposition. You can establish that those two are orthogonal, and that the sum of them is the vector that you had. It's a graduate exercise. It takes 10 or 15 minutes, but it's not. It can be done. Okay, so this can be written like u minus the projection on the normal cone. I simply use this formula to eliminate the projection onto this. Okay, so that's the first step. Then I need a second notion of convex analysis. I'm sorry for those technical aspects. I will come back to more physical things after, more related to modeling. The notion of subdifferential, I think, is very rich, even for thermodynamics. It's something that is not so commonly taught in university lectures, but I think it can be still be interesting in many, many applications. Subdifferential is an object that generalizes gradients or differential. If I have a function from a Hilbert space or Euclidean space to R, the subdifferential, I will give you the definition and then explain, is a set of directions such that psi of at some point q, psi of q plus w q, I can write it like a qh, is less than psi of q plus h, and possibly plus. This is the Fréchet subdifferential, but let me stick to that first. So what does it correspond to? If you have a function from R to R, a simple function, like that one, it might have, so basically it applies to convex function. I will consider that the function are convex. You can check that if you are at some point Q, this is the set of slopes of lines such that the line remain below the graph. So when the function is smooth, if you are here, it will be the slope of this. So you recover the derivative, okay, the standard derivative. What is interesting is that when you have, let me draw another one, like absolute value, when you have a non-smooth function, when I am here, I can have many lines that stay below the graph, okay? And actually, if this is -1, this is 1, all the slopes corresponds to the integral -1, 1. So in that case, the subdifferential of this function at 0 will be the interval -1, 1, okay? It's a multi-valued function, okay? So it generalizes, it applies to non-smooth function, and that makes it possible to write many things in non-smooth context. Let me finish by considering a very singular function that is usually called...
But you need some convexity then.
Yeah, well, you are right. Basically, usually it's defined for convex function, because if not, it might be empty. But that's why I wrote it here. Actually, if I just ask this to be verified at little o of h, then it will accept non-convexity, but smooth non-convexity, meaning that if I have this, it will be okay. You can find that here even when you are concave, it will be okay if you take actually the derivative. You will find. But what is forbidden is bad non-convexity. This is forbidden when you have something that is highly concave and singular at the same point. In that case, this will be empty. So it's still defined, but it's not usable in practice. So this will be, and that's a good point. It leads to something that I wouldn't like too much to say because it's kind of technical, but basically it will apply to my situation even if K is not convex, because K is not too far from being convex. That's what I said. And actually I will define the subdifferential of an indicatrix function, that is a function which shall, for an interval, for example, a minus 1, 1, it equal to plus infinity if x is not in the interval and 0 if x is. So in function, the graph of which is very singular, it's this segment and then in plus infinity here, something that is commonly used in constraint optimization. In that case, you can still define the subdifferential. You can check that when you are here, the subdifferential is simply 0. There is only one line. But you are here, you have many lines that are below. Of course, since here it's plus infinity, the whole line, whatever the slope is below plus infinity. And so, in that case, at this point, you have the indicatrix, the subdifferential of the indicatrix function. So at point 1 equal to, you see what it is? The set of slope of lines which remain 0 to infinity, simply. 0 to infinity. So it's well defined and it's okay. And here that would be minus infinity to 0. Okay. And yeah. What is now the last, almost the last step is when you have a convex, when you have the feasible direction and then the normal cone. It can be checked, and it's obvious in the picture, then the outward normal cone is actually the subdifferential of the indicatrix of K. So you have to imagine when you have a 2D convex, you have a function that is 0 here and plus infinity, and you have to, so this is the set of vectors such that the associated plane remains, hyperplane remains below the graph of the function. Basically, it's simply expressed, you probably know that when you have a point, Q tilde, that is projected onto Q, the fact that Q is the projection of Q tilde is characterized by the fact that the dot product between Q tilde minus Q dot any feasible direction is non-positive. So it directly gives you the polar relation between N and Q. So it can be checked easily. So, and that was important for me. So finally, what do we have? And I will soon be finished with the convex analysis things. That if I replace my NQ, and I will do something very bizarre now. That sounds very unoptimal. I will replace that by simply saying that dq over dt in u minus the subdifferential of the indicatrix of Q. You see, I had an equality. It's characterized by a projection, and I replaced by a simple inclusion. So obviously, I have something that is not optimal. It's just I'm not choosing. But what is quite bizarre in this situation is that actually I do not lose anything, and we'll see that this is actually well posed. And it has a very nice structure that I will show. Let me, yeah, I can do that now. If I consider that the desired velocity is this one, un, and uj is equal minus the gradient of d at qj, then capital U is simply the global gradient with respect to all degrees of freedom of the sum of the d. And this is, it's starting to be a bit more relevant in terms of modeling. What I am saying is that the global velocity is the gradient, minus the gradient of the sum of insatisfaction or distances to the exit, because I have a sum, an independent term. When I take the derivative with respect to q I, then I get the corresponding term, etc. So with this assumption, I have that the capital U is that. So U is a gradient, and I have the gradient and subdifferential. Well, I said that this is a generalization of the gradient. That would be quite tempting to add, to say that the sum of the subdifferential of the gradient is the gradient of the sum. You have to be careful. In general, it's not true for this nasty version of the subdifferential. That is not true that delta f plus g equals to delta f plus delta g. Of course, that would be a sum in terms of set, a sum set. But this is untrue in general, but it is true if one of them is smooth, which is the case for you, or at least not too bad. It is the case for this one. So we have that, and that's where I wanted to come to. dq over dt is minus the subdifferential of the sum of dqj I plus ik. So the problem takes a very simple form, or it might look a bit more complicated to what it was, but it actually quite nice, because it's a gradient flow. As I said, the subdifferential generalized the notion gradient. So this is really it has the form, the derivatives minus the gradient of some functional that the crowd tends to minimize globally. So it has a very simple form. And the function that tends to be minimized, simply the sum of distances to the exit, which is the sum of insatisfaction, and plus a term that puts infinity when the constraint is violated, which makes sense. You do not want the constraint to be violated, so you forbid it like that. Okay? Then I would like to talk about the Laplace operator. Oh, let me first say, before I forget, that as you told me, there will be, for those who might be interested in the tutorial this afternoon at 4:30 p.m. For the break, with Sylvain Faure and myself about the software. There will be some indication to install. I told you about that yesterday. For those who have Windows, that will be on the website in a few hours, perhaps, or yes, maybe at lunchtime. And you can come and ask me questions. And I am sorry, probably today I will finish. I will present pictures, animations tomorrow. I see that you still have half an hour.
There was a question.
Yeah, sorry.
Sorry, could you explain again why NQ is delta phi k?
Let me see. Yeah, consider the definition. I can write the definition again. Delta I k of q equal to the set of W, set that ik of q plus WH less than ik of q plus h. So I just write the definition for ik. Okay? Now I am consider a point on the boundary of k, such that this is 0. Okay? If I consider the h, so that q plus h is outside k, then I have no information, because this is finite, this is infinite. I have a tautology, this is true, no information. But when I have this h such that q plus h is in k, then this is 0, and I have 0 plus something less than 0, so this has to be non-positive. So it gives you, and of course if, well, you understand, so it gives you that. So before continuing before exhibiting the Laplace operator I wanted to show, I would like to make some remark on computation that Sylvain might told you about. This is an extension, even if we did very abstract things. In this form, it suggests an extension of the model which is funny to use in practice, and I think Sylvain, it was not in chromosim, but I think Sylvain tried to add it. It will be added soon. No, it's more like a remark, just a break in convex analysis to make some remarks on modeling. So here it's a gradient flow, so you have to imagine the crowd is Q. So in minus sum of d of Qi plus Ik. So it's really a gradient flow, meaning that if I consider this function, you could see that it has ISO values, and the crowd flows along the steepest descent direction of this function. Okay, so it gives you an interpretation. It's some kind of democratic. All the people, all the individuals have the same importance. So this is the dissatisfaction of the people, and those are individual dissatisfaction, which are that corresponds to me, and the global one is the sum of the individual dissatisfaction. So what I will show you, and Sylvain perhaps this afternoon, and me tomorrow, is that this does not work fine. It's some kind of hierarchy. People do not see each other. They just try to struggle, and they interact through this constraint. And in some time, in some situation, we'll have jams. So it will be nasty. It will not work fine. And what would be interesting is to see, is it possible to design strategies, individual strategies, in order to break those jams. And we'll see that it actually works in a very simple way by considering that I have beta I is a coefficient. If I am I consider beta I is the weight of my own dissatisfaction in the overall dissatisfaction. You see, it could even be transposed in a political context, or you see, you feel you are not happy because, I don't know, you pay too much taxes, and you shout for that, you are not happy. But you can also say, okay, I pay too much taxes, but whatever. I don't care, I'm not complaining. So basically that would be that. And you can lower the expression of your dissatisfaction by lowering your beta I, the weight you consider, you attribute to yourself in the global picture. And that's a model. I will show you the results. And you can show that by having some people lower their weights, you will improve things, you see, and you will break the jams. And I will show you, so you can try to imagine what happens. But I will show you this animation made on this assumption tomorrow.
Just to recap, so from a concrete point of view, we started from some equation. And now the gradient can be in some area in a big set, which is, I mean, it's not so well defined.
Well, actually it is, and I will perhaps, before getting to the Laplace operator, I will show you that it actually is the fact that it is well defined. So this might look like not well defined, because it is as if you have, it contains infinitely many elements, so it looks like if you have infinitely many possibilities. That is not the case. For a reason, perhaps I will make a remark, because we used a lot a theory by Maury in the 70s, which is about the same, and I think it illustrates. I need an empty glass. Sorry, I have to. Sorry. So I will make an experiment with the glass. You have a set of moving convex set in a Hilbert space. So it's a family in a Hilbert. It can be infinite dimensional, and you are a point. You want to model this situation. This is the point, and this is my This is my convex set, and I move it. And I prescribe a motion, so you don't see the point, but you can imagine. So when it does not touch, nothing happens. And when it touches, the point has to remain in the set. It's swept by the boundary of the set. How can you write this equation? Actually, it can be written. It was written in, I don't know, 78, I think. In that way, the time derivative of Q is in minus the subdifferential of the convex set at Q, meaning that your convex set is moving and your point is here, and if it moves that way nothing will happen, but if it moves downward it will sweep the point. And here we have exactly the same. That's what I wanted. This example is perhaps clearer. This doesn't look as well posed, it's just an inclusion, but it is actually. What happens is that, imagine what the interesting case, of course, you remember that when you are in the interior of the convex set, this is 0. There is only one element, so the point does not move. So the interesting part is when the convex set goes downward here. So what happens if it goes in this direction? What it says, the outward normal cone is this. So minus it says that the velocity is one of these vectors. Okay, just say that. But which one? If, of course, there is only one right velocity, that is the velocity of the boundary. You see, and if the velocity you pick is smaller than the one you should pick, then you are not swept and you end up outside of the domain. But this is not possible because this is the empty set when you are outside of the domain. So it's forbidden by the equation itself. And if you go too fast, if your velocity, instantaneous velocity, is too quick, then you do not stick anymore to the boundary. So instantaneously, you are in the interior and you stop immediately because your velocity is 0, you see? So it's a bit bizarre, but it actually, there is a uniqueness reserved. There is no way you can escape that. It defines the velocity, even if it looks like an inclusion. And that's a bit what happens in practice for this, and I will show you. Perhaps it's clearer that way. If I consider yeah, I will write it dq over dt in u minus. It's perhaps clearer if I present a numerical algorithm that will be used for that. That was already actually proposed by Maury in the 70s, numerical algorithm. You say Q, so you just take time derivative, well, with a finite difference spirit, and you take the velocity u at time k is minus d ek, and you write an implicit scheme. So typically, if the problem is actually ill-posed, this will be ill-posed too. And this, I'm claiming that this is actually simple. There is a remark that you can do that I already made informally, is that in this situation, you have that Q is the projection of Q tilde on K, if and only if Q tilde minus Q is in the outward normal cone, NK. That is NQ, that is the subdifferential of K. Okay? What I'm saying that you see Q is the projection of Q tilde, if only if Q tilde, so Q tilde minus Q, is actually, this is the proper characterization of the projection. It belongs to that. So actually this characterizes the fact that Q plus 1, it's written, yeah, the projected point is Q here. So it basically tells you that Qk plus tau uk minus qk plus 1 is in the subdifferential of qk plus 1. And this is exactly what happens here, where Q, the role of Q is placed by qk plus 1. And this tells you that qk plus 1 is the projection of this. So in a bizarre way, it ends up, even if it was written in an implicit way, it ends up to be an explicit scheme qk plus 1 equals to the projection onto k of qk plus tau uk. And this is very, I don't know if you already use things like that when you have an evolution problem with a constraint. It's quite common, for example, for Navier-Stokes equation, when you have an incompressibility constraint. You have those kind of prediction correction schemes or projection schemes simply. You have a predicted, so you use an Euler scheme without caring about the constraint. And then you get something that might be forbidden, you simply project it. Okay? It can also be seen, since it's a gradient flow, as a projection gradient flow method that you might have used in computation. So it actually takes a simple form. It's actually fully explicit. Okay?
So, Bertrand, does it mean we could replace the belong to by an equality?
No, because this is a set. Because you don't know it, you don't know which element it just belongs to, but it tells you that if you do not pick the right one, you are dead. But I will not tell you which one it is. You have to determine it, you see. No, it's, you cannot, well, it has, well, the first model was purely, perhaps what you are saying is you prefer the first expression because it's fully explicit. The PCQ, this gives you, this is no problem, the projection is uniquely defined. And this is a bit trickier. It's not this equation, but it's this one, for example, or this one. But it reveals the structure, and it can be extended. So, and if you want to study it theoretically, it's much more convenient. You have many works on that kind of equation, whereas this is not clear. The structure of this one is not clear. That's why. Yeah.
So just to so I understand correctly, so even if this subdifferential is like multi-directional, like just like in a corner, as long as you're satisfying this at each t, the path you pick is unique. That's the statement, right?
What do you say at the end?
As long as you satisfy this at every t, the path you pick is unique.
Yeah.
This is the statement. Okay.
Yeah. And you have an existence and uniqueness result for this kind of equation if you assume that your convex set for this does not move too badly, like in a continuous way for the Hausdorff distance. And then you have a uniqueness, and what I tried of a function that is continuous, a q of t that is continuous. You have to pay attention to the fact that you want to avoid situation, for example, where you have it moves that way, and then if you accept to have impulses, to have non-continuous position, it could go directly in a it could be solution to this equation in a very weak sense by just dropping like a fly to the, but if you look for a continuous solution, then you will say, you can show that this is unique.
But if you like discretize, it seems like this shouldn't, how do I say it, like this multi, the fact that you pick from a set seems like it should matter a lot, potentially. And
no, when you do, actually, to build solution, what he does is something like that. You have a position, then you move the set and you project it on the set. And the algorithm is fully deterministic. It's fully, there is no inclusion. So basically, what's your question? That you are bothered by the fact that I wrote it as an inclusion, whereas the problem is it's difficult to write if you know the velocity of the set. This is a moving set. Even the notion of velocity of a set is not clearly defined. So it makes it possible to write this very complicated equation in a simple way. And even if in the case of crowd motion, I might write it in a simpler and more explicit way, here there is really no possibility to write it in a different way.
I see. So you discretize, you just pick one direction somewhat.
No, it's picked by the fact that it is projected. I do not choose, but yeah. But do not hesitate. I feel that I was not so clear. Do not hesitate to come back if that's not clear. So for it, I think I have time to talk about Laplacian, and then that will be the. Use this one. So the question, where is the Laplacian? I promised you a Laplacian that will play a very significant role in how things go. So let me get back to my abstract. I will need some few abstract things. I have at some point I have a cone of feasible velocity and the outward normal cone dq, that is CQ polar. And how is it defined? CQ, if you remember, is the set of V such that when you have dij q equals 0, you have eij dot vi minus vj less than 0. So this can be seen as so it's a linear condition on the velocity. It can be written bv less than 0. Less than 0 is an element-wise meaning for each element of these vectors. Okay, and the number of constraints that I have corresponds to the number of couple of particles that are in contact. So at some instance, it can be written, this can be written bv dot q is less than 0 for all q in R plus. It can be written in a dual way. You will see that it makes sense, where this is the number of contacts. So it can be seen like that. I like this picture. So here I am in the primal set. Here it corresponds to R to the 2n, the number of degrees of freedom for particles. Here I am in the world of contacts, R to the nc. And this is the pressure that are positive. I put them here. Lambda plus, it's simply R plus to the nc. And lambda plus polar is simply the polar of the vectors with non-negative is simply the cone of vectors with non-positive. And what I'm saying is that, perhaps I'm going not to spend too much time, but it's explained in one of the papers for those who like abstracting. It's the nicest way to build a Laplacian, actually. So CQ is defined as this is B, my matrix B, has the reciprocal image of, so B minus 1 of lambda plus 0. And there is a property which I will not establish completely. I have, I think I will miss time, but is that the polar of CQ, if you remember, when we had equality constraint, we had that the kernel of B orthogonal equals the image of B star. And what I would like to establish is the unilateral version of that. So this is what you learned in undergraduate courses. And now B is still the same B, but instead of getting the kernel of B, okay, I get the reciprocal image of non-zero, but a cone that is itself the polar of some cone. So how would you can you guess what I would like to write here? Here I have B star, the adjoint operator of the transpose matrix, if you wish. What I'm saying is the polar cone of this is, you see how I can close the diagram? So B takes this cone and gets CQ. And what will play the role of the image of B star? That will be actually B star of something. That is B star of lambda plus, yes. So the notation are not very easy to follow, perhaps, but and I will not prove that completely, but let me just check that at least one inclusion is trivial. If I considered an element of this set, so if I consider Q in lambda plus and V in CQ, and I considered B star Q scalar V, I just use the definition of the joints. It's V scalar, sorry, it's Q, it's got B Q, B V, oh, sorry. But since Q is in lambda plus and V is in CQ, this is by definition of CQ, this is non-positive. So this is, it means that B star Q is actually in the polar cone of CQ. Sorry, it's not very, well, if you are not used to the notation, that's easy to follow, but it's quite elementary actually to check. So it means that this image is actually, and to show that this is actually the set, you have to show that the cone, it's closed actually, but in finite dimensional situation, it's not too difficult to show. And then you have to choose to show that this is actually an identity, and this is a consequence of Hahn-Barnard's theorem. For those who might know, it's a proof in convex analysis that is quite straightforward, but using quite a fine argument. Okay, so we have this, which is the unilateral counterpart of what we had for equality constraint. And now I will have this Laplace operator appear.
So sorry, yeah. Just a lot to absorb. Just wanted to clarify this. Yeah, so this lambda plus. This is just the intersection between the allowed and disallowed.
Sorry. Where is my no, lambda plus. A simply way. This is quite general actually, but in the setting I present, it's just a way to express those constraints, element-wise constraint. I'm just saying that this is non-positive if and only if I take the dot product with any vectors in this R plus to the NC, then this is non-positive. Okay? And what I'm calling lambda plus is this. Is the set of, actually you can see at the set of pressures between when you have in a crowd, to get back to more concrete thing, when you are in a crowd, each time you have a contact, you will have some multiplier, Lagrange multiplier that is positive, and that will correspond in practice to the force between people. That is positive, people do not stick to each other. But, at first it appears as a way to express in dual way some constraints. So lambda plus is this, and what I use is the fact that the polar cone of this is very simple. You see all the polar, like in R, lambda plus in R2 is this, just this cone. And the polar cone of lambda plus is this one. So it's minus lambda plus. It's a very typical situation, very singular situation. Lambda plus polar is minus lambda plus. So the set of vectors, with non-positive. Okay? So I don't know if it's clear. Things.
It's a little bit clearer.
A little bit clearer. Do not hesitate to. I'm feel a bit guilty, but I know that this is not very easy to swallow if you are not used to that kind of thing. But I try to show it's worth it, because it can be applied in many interesting and real life situation or physical situation, and I will see that it's a way to get to this Laplace operator if it's a motivation. So that's what I will spend the last minutes to do that. So what is B actually? So I will do it in 1D to see that in 1D, of course, the model is not very interesting, but I have people on the line. They all touch each other. Perhaps I will, let me write this, sorry, CQ equals to B star. Let me get back to the fact that I had the decomposition of capital U, the desired velocity, as the projection of on CQ plus the projection on CQ polar. So this is u, the actual velocity of the population, and this is in an element of the polar. And what I just show here is that this can be written B star of some P, that is P is in lambda plus, that is R plus to the NC, okay? It's the set of pressure. That's what I showed almost fully, but not completely. But okay, so finally, what do I have? I write that U plus B star P equals capital U, and I had that BU is less than 0. So I end up with a, well, mathematician calls a saddle point formulation of the problem, because there is a saddle point hidden in here. And it takes the form of like Darcy problem, Stokes problem, many problems, a bit Navier-Stokes if you add time dependency. And the only thing is that this is a inequality. You know a Darcy model, I guess, if you want to model flow in soils, for example. U, so it really has this form, divergence U equals 0. Here it's about the same. The only difference is that here I have inequality. Okay, but it has the same structure. So it suggests that B plays the role of minus the divergence, and that B star plays the role of the gradient. Yeah, I would like to show that by considering this situation, we have people, when we'll go to the lunch, you have people like here, imagine that they touch. You have some velocity field that it's typically, it's interesting when there is some action. So here a small desired velocity, and then like bullies at the end that try to push people. I'm not looking at anyone. What happens? What is B in this situation? Well, B expresses just if you index particles from here to here, 1, 2, it will have I think it's 1 minus 1 and then 0 and then 1 minus 1. It's a slightly rectangular matrix. That way. You see, basically you make the difference between the two velocity. It has to be non-negative in order not to overlap. Okay, so this is B. So B star, you imagine, you take the transposed. And then when you perform, what is interesting here when you have this system is that if you consider that all constraints are active, meaning that I should have written here the fact that you also have this, what is called a complementary condition, BU dot P equals 0. It basically corresponds to the fact that when you project, we have those two projections, those two vectors, they are orthogonal. And it's important, it basically tells you, and it's important from a modeling standpoint, that when the constraint is not saturated, for some contact, you have that the quantity that should be non-positive, it is actually negative, strictly negative. Then in that case, there shouldn't be any pressure. It just means that if you don't need pressure to ensure the constraint, the pressure should be 0. It's exactly, actually, it's a bit like if you want to model the fact that this has to stay on the table, you can write that by minimizing the potential energy under the constraint that this remains at a non-negative altitude. And that you have a saddle point formulation with a Lagrange multiplier. It basically tells you that if the thing does not touch the table, then the pressure should be 0, because the table is not allowed to act at a distance to the object. So, but if you consider only constraints that are active, meaning that you really squeeze your population, that is the interesting case. In that case, you can eliminate the velocity. You see U is capital U minus B star P, and then you replace it here. And when the whole constraint is activated, when the pressure is non-zero, it means that you actually have BU equals 0. So you can really eliminate, and you end up with B star P equals to BU. And I'm claiming that this is actually a Poisson equation. This is a discrete Poisson equation. Why? Because if you consider B, the matrix B, and B star, you put B star, you can imagine like in your head the mat product, and you end up with this matrix. Okay, which is a discrete Laplace operator. So there is actually, at least in 1D, a discrete Laplace underlying. And what we'll see tomorrow is that it's much more complicated in 2D. The interesting situation, of course, the 2D situation. And there is still something that looks like a Laplace operator, but with very bad properties. That will explain the bad, bizarre behaviors of crowds, but which are realistics. And that will be all for today. Thank you.
Thank you very much. Are there any questions?
So you mentioned this beta parameter. I guess you could envisage having a parameter next to the ik as well. You know, people can somehow squeeze in a bit.
Yeah, we can some sort of relax the constraint. Yeah, that might be possible. What happens in practice, actually, people, they do not choose to relax the constraint. They are just crushed. And but you can. That gets back to the question asked by Thierry. That would it be possible to relax this constraint to put some interaction forth, which would make sense for computation. The theory is more difficult to have a Laplace. I love Laplacians, so to have it appear and to see. And I will try to convince you that it's interesting to have that to understand really what the bizarre behavior.
Still having hard spheres, but the hard sphere diameter changing.
Changes. Okay. Okay. It's we'll lose the structure of the matter. We'll really have to change it. That might be possible, but in some way you change K as in the Morrow's sweeping process. You can change the convex, the feasible set by changing the constraint, like you change the radii. But you have to find a rule for that. That might be interesting. If you prescribe the change, that could work mathematically. But the problem is that you will find a proper, we can discuss about that, but a proper way. But that might depend on the pressure. You can say that when the pressure is high, then the radius is reduced. And that leads to a problem which I do not know, but it could be written properly, I think. Yeah.
Are there any more questions? I was wondering, so this gradient flow structure is not depending so much on the part with D. I mean, you could have further maybe interaction or that.
Yeah, you could have. It might be difficult to explain, to interpret, but you might have a strong coupling between people. For example, you can consider that a family, for example, they want to minimize their distances they want, and but then the consequence would be that it will have some effect on if I have two members of the same family, some kind of attraction forces of that both of which are submitted to. Does it make sense? It depends. You could, but that would be possible, but it will have consequences on your model. What would be in a family, for example, you could consider that the interactions are not symmetric. You have children and parents. Perhaps the parents they want to keep track of their children, and the children they forget. So the interaction is not necessarily symmetric. So in terms of modeling, you have to be careful to what it. But basically, yeah, with this structure, that's what is very rich. Also, you can put all the ingredients you want in terms of dissatisfaction, say, and you see what happens. Yeah, sure.
So maybe we're going to stop for now. Let me remind you that if you want to see all this in practice, so this afternoon at 4:30 there will be further talk by Sylvain and Bertrand Maury. And you can find the links how to install their software. Thank you. I was looking for the word. How to install the software. You go on the program, and just next to the name of the title of the session, there is a little button on the right. You click on it, and then you see the abstracts. And by the way, also Bertrand sent me some references, and you just click on the abstract of this session, and you will have access also to the references. It's on the program. So we resume at 11:20 for the next talk. Thank you very much.